quantum sensors, or sometimes we call them PAR sensors, photosynthetically active radiation sensors. They look the same, but instead of being designed to measure all of the short wavelengths from the sun or an electric light, they only measure the photosynthetically active wavelengths. And that's typically defined as 400 to 700 nanometers. The same wavelengths that the human eye sees are the same wavelengths that drive photosynthesis in plants. So it's an often used measurement in plant research because it tells us how much radiation is available or how many photons are available to make photosynthesis happen. And there is multiple radiation sources available used to grow plants. I'm showing some here. Sun, lots of different electric lights. Nowadays, LEDs, light-emitting diodes, are becoming more and more common. So this is actually a photograph taken from Bruce's lab at Utah State University. And they've got all these little growth chambers, each one with a different colored LED or a different combination of colored LEDs in them to see what kind of effects different color treatments have on plant growth and plant morphology. I keep pressing the wrong button. So LEDs are becoming more and more common all the time, especially in research applications. LEDs are often narrow band, meaning they only output a narrow range of wavelengths, whereas radiation sources like the sun or some of these electric lights are broadband. They output a lot of radiation across the photosynthetically active range. But the main point that I want to make here is that accurate photosynthetically active radiation, or PAR measurements, are required for a host of applications, especially if we're interested in photosynthesis. So before we start talking about the sensors, here's just a few definitions. You probably have heard these terms before and seen them defined, but it always helps to review a little bit. So I already mentioned that photosynthetically active radiation is the radiation that drives photosynthesis. Photon flux density is just the number of photons that flow through a unit area per unit time. And we're just counting photons, basically. And so we either count the micromoles of photons per meter squared per second. That's an instantaneous unit that we use. Or we count the moles of photons per meter squared per day on a daily time scale. So that's how we characterize the flux of photons. The photosynthetic photon flux density, PPFD, is just the photon flux density integrated over our photosynthetically active range, so 400 to 700 nanometer wavelength range. And so when we have a quantum sensor or a PAR sensor, one of these guys, this is the number that it's measuring right here. And they put out this unit, so it measures the micromoles of photons per meter squared per second. So basically the incident photons on the detector. And then when we integrate that number over a whole day, we get the moles of photons per meter squared per day. The yield photon flux density is kind of like the photosynthetic photon flux density, but instead of just integrating over the 400 to 700 nanometer range, to get yield photon flux, we actually weight the photon flux by the plant response to photons, and then we sum it up. And this one will become a lot more clear on my next slide, because I will show you a graph that illustrates the difference between this one and this one. And so a quantum sensor is this thing. It's just the instrument that we use to measure PPFD. And the reason that we often call them quantum sensors is because one photon is a single quantum of radiation. But quantum sensor can be kind of a confusing term, I think. Nowadays, you often hear them called PAR sensors because they are measuring photosynthetically active radiation. But PAR sensor and quantum sensor mean the exact same thing. So here's the graph that I mentioned when I was describing the difference between photosynthetic photon flux and yield photon flux. So wavelength on the x-axis, and then just relative quantum yield or the response to photons on the y-axis. And so the green line is actually measured data from a number of different places. I listed some of the publications here. So Keith McCree at Texas A&M University was the first to do this back in the early 70s, and then others followed up and found similar data. But what he did is he took a leaf and he measured the photosynthetic response, or basically how much carbon did that leaf uptake at each wavelength of light. And he used a light with specific filters over the top of it to give him really narrow wavelength ranges. And he just measured the carbon uptake of single leaves as a function of wavelength. And he found that the photosynthetic response actually looked like the green line. So the plant leaves respond a little bit more to blue radiation than they do green radiation, and they're most sensitive or most responsive to the red radiation. But the data that McCree and others measured for single leaves, we have to remember that it was in the laboratory. It was plants grown under controlled conditions in many cases. I think they also measured field plants. It was a low light environment, and again, it was single leaves. So a more useful and universal definition of photosynthetically active radiation is, rather than trying to weight measurements of PAR by this green line, we just assume that all the photons between 400 and 700 nanometers are equally efficient at making photosynthesis happen in plant leaves. And so the universally accepted definition of PAR is what we call this defined plant photosynthetic response, where we just give equal weight to all the photons within the 400 to 700 range, and we don't give any weight to photons outside the 400 to 700 nanometer range, and we use that as our definition of photosynthetically active radiation. And so PAR sensors, these kind of devices, should have a spectral response or a sensitivity that matches this black line as close as they can. And so there are really a couple of options for measuring PAR. One is to use a quantum sensor like this. And it's a broadband device, meaning it gives you a single signal, one number. An analog device means it would output voltage that represents the sum of all of the radiation that's incident on this detector. And again, it should be the sum of all of the radiation between 400 and 700 nanometers. And so that number, that voltage that it outputs, is weighted by the spectral sensitivity of the sensor itself. Right? So you have a filter, and the purpose of the filter in front of the photon detector is to try to give us the best match that we can to 400 to 700 nanometers. And then we have a single detector that gives us an output that should be proportional to PAR. And so the spectral response of the sensor is dependent on the transmission of the filter and the sensitivity of the underlying detector. Alternatively, rather than using a quantum sensor for PAR measurement, we could use a spectroradiometer. These are hyperspectral devices, meaning we're getting signals at multiple wavelengths. And so you actually can get spectroradiometers that give you a measurement at every single nanometer within the 400 to 700 nanometer range. That would be quite fine resolution. Oftentimes they give you a measurement at every 5 nanometers, for example. But the point is, you're actually getting a measurement at multiple positions across the wavelength range of interest. And so a quantum sensor only gives you PAR. A spectroradiometer gives you both PAR and the spectrum. So not only do you get photosynthetically active radiation, but you get the shape of the spectrum. And in some applications, that might be useful. And so here the detector array determines the spectral response. You know, a spectroradiometer is in practice, it's a relatively simple device. You have a prism or maybe a diffraction grating where the light enters the unit, And that prism or diffraction grating is actually separating the light into the individual wavelengths. And then somewhere behind that prism, you have a whole array of detectors that measures the intensity of the individual wavelengths. So you get multiple signals. So it looks like a relatively simple device on paper, but in practice they can be quite complicated. And so the only thing that really determines the spectral response or the sensitivity of a spectroradiometer is how well is it calibrated. If we can accurately calibrate each of the wavelengths, then we have an accurate quantum sensor independent of the light source that we're trying to measure. And so there's lots of different options for quantum sensors. Here I'm showing you some of the more common commercially available quantum sensors and how well their spectral sensitivity or their response to photons matches our definition of photosynthetic radiation. So the black line is what we're trying to match because that's our definition of the photosynthetic photons. And then the colored lines, the blue and red lines, are the actual sensitivities of some of the different sensors that are available on the market. So Kippenzonen has a sensor, Sky Instruments has a sensor, Lycor has a couple. The model LI190R has now been replaced by a newer model the LI190 has now been replaced by a newer model from Lycor called the LI190R. At Apogee we build a couple different models. The SQ110 is the one that we've sold for years, and it's still available. And the SQ500 is a new model that is a better match to the photosynthetic photon flux weighting factors. So having this information, we can actually now make estimates of what kind of errors we can expect when we use these sensors for different light sources, meaning Bruce talked a little bit about how the solar spectrum can change for clear versus cloudy conditions. So if we calibrate these sensors in clear conditions, for example, and we know that none of them have a perfect match to our definition of photosynthesis, we can expect some errors when we try to use them in cloudy conditions. Or for example, if they were calibrated in the laboratory under an electric light, what happens when we try to use them for measurements under a different electric light? Or what happens when we take them out of the laboratory and try to use them for measurements in sunlight? All we have to know, we need 3 pieces of information basically to estimate spectral errors. And that is, we need to know the spectral response of the sensor. We have that information here. We need to know the spectral output of the radiation source that was used to calibrate the sensor. And then we need to know the spectral output of the radiation source that we're trying to measure. So to better illustrate that, let's just take an example. And so you can see here's the spectral response of the Apogee model SQ110. This is the traditional Apogee quantum sensor that's been available for several years. And you can see that it's not a great match to our definition of photosynthetic radiation. That we measure some of the UV. It's not as sensitive to the blue as it needs to be. And it misses some of this red radiation out here when we get close to 700. So this mismatch between the actual sensor response to photons and our definition of photosynthetic radiation is going to cause spectral errors. And kind of an extreme example, let's say we were measuring an LED that was a blue and red mix where the red peak was like 660 or 670 nanometers. You can see there's a lot of output from this LED that's beyond the sensitivity range of the sensor. That means the sensor's not going to count those photons because it's not sensitive to them, and it will cause spectral error. So there's an equation we can use to actually calculate spectral errors, and as I mentioned previously, the only bits of information that we need, this S is the spectral sensitivity of the sensor. In this example, it would be the blue line. The I calibration is the spectral output of the light source we use to calibrate the sensor. It could be the sun, it could be an electric light. And then this I measurement is the spectral output of the lamp that we're trying to measure, right? It might be this LED, for example. So what I'm about to show you is error calculations using this equation for all 6 of these quantum sensors that I have spectral information for right here. And there you go. And so the table shows data where we use sunlight on a clear day as the calibration source, and so all of them have 0 error under sunlight. And you can see what kind of errors they have for a whole bunch of other light sources. So we've got sun spectrum on a cloudy day, a sun spectrum that's reflected from a grass canopy. So you can actually, in addition to measuring incoming radiation, some applications you might want to invert the quantum sensor like this and measure reflected radiation from the plant canopy. If you have a measurement of incoming radiation and a measurement of reflected radiation, it tells you how much of the photosynthetic radiation is being absorbed by the plants at the surface. And so Bruce just mentioned in the previous talk that if this were a silicon cell pyranometer, you can't invert it like that and make measurements of the surface because there's large spectral errors that are associated with doing that. And he showed a table of some of those errors. Using a quantum sensor, however, one of these PAR sensors that's designed to measure photosynthetic radiation instead of solar radiation, you can take it and invert it like this. And these numbers here, reflected from glass, gives you an idea of what kind of error you can expect when you invert a quantum sensor. So oftentimes, and I'm going to talk about this particular application in a little bit more detail in a minute, we want to put quantum sensors underneath plant canopies and measure how much of the photosynthetic radiation is transmitted through the plant canopy. So here's the kind of errors you can expect if you measure underneath plant canopies. This is data for a wheat canopy. I think I failed to mention that all of the numbers that you see here are percentages, so not actual radiation units, so not micromoles per meter squared per second, but percentages. And then we have a whole list of electric lights that people might use in a greenhouse or a growth chamber environment. So a couple things that you can see by looking at the data in this table is that all of them work quite well for most of the radiation sources on there, except for the Apogee model SQ110. Some of these LEDs, you can see the errors get pretty large. That's because of the data I showed you on the previous table. It doesn't have an excellent match to the photosynthetic definition, or the definition of photosynthetic radiation. And so you want to be careful using quantum sensors for certain radiation sources. You want to make sure that they are going to capture the photons that you're trying to capture. You'll notice of the other sensors, some of the worst errors also tend to be LEDs, right? So here's a 3.8 and 3.6%. That's an LED. A 3% over there, that's an LED. LEDs are tricky to measure, so for those of you that are working in greenhouses and measuring LEDs, sometimes the best option for that might be a spectroradiometer. And so, as I mentioned when I was talking about the differences between quantum sensors and spectroradiometers, if your spectroradiometer is calibrated accurately, because it's measuring all of the wavelengths individually, then spectral error doesn't exist. We don't have to worry about spectral error with a spectroradiometer. The main difference, so you might be asking, well, if this is the case, why would I ever use a quantum sensor to measure PAR? Wouldn't I just use a spectroradiometer every time? The difference is the price tag. Quantum sensors tend to be in the low hundreds to maybe the mid hundreds in terms of cost. Spectroradiometers tend to be an order of magnitude higher. They're in the thousands, the low thousands to maybe even the mid to higher thousands. So that's the real difference. Quantum sensors are often the measurement of choice because they give you accuracy that's good enough for the application, and they're much lower cost. Okay, so this is just a brief comparison of everything we've covered up to this point. Quantum sensors are subject to spectral error. Spectroradiometers are not if they're calibrated accurately. Quantum sensors give you a broadband measurement, meaning one number or one signal that's proportional to par, so you can only get par from a quantum sensor. A spectroradiometer, not only do you get par, you get the spectrum if the spectrum is required. And then I just talked about the differences in price. So a couple more review points. There's lots of commercial quantum sensors available, and I showed at least 6 of them and their spectral errors. And many of them have minimal errors, less than 5% when measuring lots of different light sources. And then remember, par is almost universally reported as photosynthetic photon flux density in units of micromoles per meter squared per second, but it can be converted to other units if the spectrum is known. So the reason that I put this point up here is often we get people that contact us that they need measurements in units of watts per meter squared, or even units of lumens per meter squared, lux on occasion. You know, these units aren't often used in environmental applications in plant science, but on occasion that they are. And so you can convert PPFD measurements from a quantum sensor to other units if you know the spectrum. It's possible to do that. Bruce showed a table like this for Apogee pyranometers. Here's similar information for Apogee quantum sensors. Just some specifications to give you an idea of the performance. So the directional response, or the cosine response for a quantum sensor, is very, very similar to the cosine response for a pyranometer. The temperature response is also similar. The stability is a little bit better for the quantum sensors that we tested, and the calibration uncertainty is listed there. Let's skip over that summary slide just because we've pretty much discussed everything already. So I mentioned I wanted to talk about a specific application, intercepted radiation. And I want to show you something really quick before we go through the slides. I thought it was interesting. This is a little brochure from Western Sydney University that I picked up yesterday here in the Hawkesbury Institute. And there's a part, I'll blow it up on the document camera so you can see it. Here we go. There it is. So this is actually a picture and a short caption from the brochure that I found here at the Institute yesterday, and it says, "This photosynthetically active radiation sensor measures light intensity below the canopy. These are combined with sensors above the canopy to estimate how much shading is occurring, which correlates to the amount of leaf area." So one application of these PAR measurements is above canopy and below canopy measurements to try to estimate how much radiation is being absorbed by the plant canopy and how much is being transmitted to the soil surface. And from that information, not only does it tell us how much of the photosynthetic radiation are the plants absorbing, but it also tells us something about the leaf area, you know, in between the sensor that's above the canopy and the sensor that's below the canopy. And so this application is actually taking place right here at this institute, and I'll talk a little bit about it for just a second. Now let's switch back over to the slides. And so I actually have a picture here of what's called, hang on, it always does a little hiccup before it comes back. I have a picture of what's called a line quantum sensor, and making a measurement of the radiation underneath a corn canopy. So here I'm showing a crop canopy, but you could do this for a pasture or an orchard or a forest, whatever you were interested in. And so a line quantum sensor is just like this quantum sensor, except for there are multiple sensors along the line. This specific one has 10 sensors, so each one of these circles that you see here is a sensor. Those 10 sensors are spread along a bar that's approximately 70 centimeters long. So the reason that you want multiple sensors when you make under canopy measurements is that and you can see it in this picture, the light environment underneath a plant canopy is not uniform. So you can see these two sensors up here are in a light fleck where they're actually getting a lot of sunlight. All the rest of the sensors are in the shade. And so when you make measurements of radiation underneath the canopy with the line quantum sensor, remember that the radiation is often non-uniform. It works really well to measure with the line quantum sensor because then you get an average along the length of the line. And radiation under the canopy should be measured in multiple locations because it's non-uniform. So it often works best to make a measurement in one location, move it, and make a measurement in another location, move it, make a measurement in another location, and average the numbers. That way you get a pretty representative idea of what the mean radiation environment is like underneath the plant canopy, and also how variable it is. So just to give you an idea, here the equations are pretty simple. Where the intercepted radiation, you just measure the photosynthetic radiation above the canopy and below the canopy. The transmittance is the below canopy measurement divided by the above canopy measurement. And then the fraction intercepted is 1 minus the transmittance. And so you have to have a quantum sensor above the plants and then a line quantum sensor below the plants. Pretty straightforward, and then you just plug the numbers in to get intercepted radiation, transmittance, and the fraction of intercepted radiation. And so for a relatively sparse canopy like this one here, the leaf area index might be roughly 1 meter squared of leaf area per meter squared of ground area. In the middle of the day, on a sunny day, the transmittance would be about 50%, where roughly half of the sunlight that you're measuring above the canopy would actually get transmitted below the canopy. If we were to move to something like this, where we have a much higher leaf area index, say something on the order of 5 meters squared per meter squared, in the middle of the day on a sunny day, the transmittance would be about an order of magnitude lower. Closer to 5% of the radiation above the canopy is going to get transmitted to the soil below the canopy. And so once we have this information, once we have the transmittance, we can actually get some sense of the leaf area index if that's what we're interested in. And so this shows you 4 different plots of transmittance as a function of leaf area index. And this would be for a solar zenith angle of 20 degrees on a relatively clear day. The reason that we have 4 different lines and they're spaced like that is not only does the leaf area influence the transmittance, but the orientation of the leaves can also have a big impact on the transmittance. And so the green line would represent a canopy where most of the leaves are positioned horizontally, whereas the red line would represent a canopy where most of the leaves are positioned vertically. Turns out that most plant canopies, I'm not as familiar with forests, but crops tend to be somewhere near these 2 black lines, where you have a fairly even distribution of both horizontal and vertical leaves. And so there's what the data look like now at a solar zenith angle of 60 degrees. I'll toggle back once just so you can see. It also shows you that not only does leaf area and the position or the orientation of the leaves have a big influence on transmittance, but so does the position of the sun. Right? And so if we know something about the leaf angle distribution, or if we can make measurements when all of the lines are, converged or close to one another, we can get a good idea of the leaf area index of our canopy of interest. And so I've actually been working on a research project in an alfalfa canopy over the summer, and we wanted to get some idea of the leaf area index as a function of the height of the plant canopy. And so we made a couple measurements in the recent past at different heights. One was here when the alfalfa was 17 centimeters tall. We got a transmission of about 20%. That would correspond to a leaf area of about 1.7 to 1.8 meters squared per meter squared. Then we made measurements later in the growing season when the alfalfa was much taller. It was about 64 centimeters tall, and we got a transmittance that was an order of magnitude lower. That would correspond to a leaf area of about 4.7 or 4.8 meters squared per meter squared. It turns out that these estimates of leaf area, 1.8 for a 17 centimeter alfalfa and 4.7 for 64 centimeter alfalfa, are very close to actual values. If we were to sample the leaves, destructively sample the leaves and measure the leaf area, we would get very similar numbers. And so you can, if you're careful with the measurements, use transmittance data from quantum sensors measuring above and below the canopy to get some idea of leaf area and canopy architecture. So real quick, I mentioned reflected radiation a minute ago, so I won't spend too much time on this slide. But you can also measure reflected radiation using quantum sensors, where you orient one up and one down, and then the one measuring the reflectance, if you take the ratio of those two numbers, you get the reflectance, and 1 minus that number gives you the amount of, or the fraction of the photosynthetic radiation that was absorbed by the plant canopy. So, gives you an idea of how much radiation is being absorbed by the plant canopy and used for photosynthesis. And so just a couple points here. The sensor should be level for both the upward and downward measurements. The upward measurement, it's obvious why that one has to be level. Bruce talked about this in his presentation. If it's tilted a little bit one way or the other, you can actually get pretty significant errors on a sunny day. If you're tilted a little bit towards the sun, it's actually going to read quite a bit higher than it should if it was level. And if it happens to be not level and tilted a little bit away from the sun, you'll get a measurement that's a lot lower than it should be. The reason it's important to make sure the downward one is close to level as well is so that in a place like Logan, Utah, where Bruce and I come from, it wouldn't matter that much because the entire valley where we live is surrounded by tall mountains. But in places where it's flat, when the sun first comes up over the horizon, you want to make sure that the direct sunlight doesn't hit the diffuser. And if it's tilted a little bit one way or the other, in the early morning or late evening hours, you might actually get some direct sunlight hitting the sensor that's not reflected from the surface. So you just want to be careful that you level both sensors. I believe that's all I had for the quantum sensors. Any questions about photosynthetically active radiation? Measurements above canopy or below canopy?
We were using reflective mulch to reflect the light back up into the bottom of the tree. But the ground is quite slow. Should the downwind ones be at right angles to the ground, or should we let?
Well, I think that really depends on you and what you want to quantify for your application. And I think, in my opinion, and I'm not a tree expert, you would want to know, probably still a horizontal measurement, because the bottom of the tree canopy is
parallel with the ground.
Roughly parallel to the ground, correct?
Yeah, so they're right angles to the ground.
Oh, right angle, okay. There you go. I think that, it depends on which orientation you're interested in quantifying the radiation. I don't know that there's a right or wrong answer to that question. You could do either. But any others? Yeah, Bruce.
I mentioned that people have long predicted photosynthetic radiation from shortwave. If you measure one and you can predict the other. Mark and I just wrote a book chapter for American Society of Agronomy on shortwave radiation, photosynthetic, and UV. And that chapter talks about the challenges of predicting one from the other. It's in more detail than we've been through here, but that's a forthcoming book chapter about ratios of radiation.
Right. This is actually a really good point that, historically weather stations have never had quantum sensors on them. Quantum sensors have really only been in existence since, I guess, the early 1970s, but they've only really been in widespread use for maybe the past few years. And so it's not common that you would find a weather station that has a pyranometer on it to give you solar radiation and the quantum sensor on it to give you photosynthetically active radiation. But there could be, applications where you need to take weather data from a weather station, and one of the pieces of information that you need is the photosynthetically active radiation. And so Bruce is correct. You can actually estimate photosynthetically active radiation from pyranometer measurements of solar radiation. If you're interested in doing that, again, grab my card and send me an email. I can provide you with some information. The model that allows you to calculate photosynthetic photon flux from solar radiation measurements is pretty simple, but there's some coefficients in there that can introduce some error, and the coefficients are also dependent on the sky conditions. So if you're interested in that or want more detail, I'll gladly talk to you. Just see me afterwards or grab my card. Any other comments or questions? I have just a couple slides that I'll mention UV briefly. I can do those now. I think lunch was supposed to be 12:30, so we're about right on schedule. I'll just chat about UV real quick. I don't have a lot to say. Oh, I actually failed to mention one point. Sorry about that. So, if you're anxiously awaiting to get to UV, we'll get there in one second. I forgot this last point on my slide. So you can actually measure reflected radiation using a single sensor if you want to. Like what I said before is you'd have one mounted like this that's level, and then a second one mounted like this that was level. That's how you would do it if you wanted to continuously measure it over the course of a growing season. But if you want to do this instantaneously, you can actually take your sensor and measure it in this position, and then flip it upside down and measure it in this position. Just be careful when you do that during the time interval that it's here to here, that the radiation doesn't change. Otherwise, you'll get an incorrect number because the incoming number changed. And so on a clear, sunny day, no problem. Measure here, flip it over and level it, and measure here. But on a day when it's intermittently cloudy, you have to be really careful doing something like that. And I probably wouldn't recommend it because the clouds can actually change the incoming radiation very quickly. You can put a sensor, and maybe we can even do this at lunch if you're interested, because I think it kind of is intermittently cloudy today. We can go plug this USB sensor into a computer, and you can watch how dynamic the radiation is on a cloudy day. It changes rapidly and sometimes by large amounts. And so if it's cloudy, especially intermittently cloudy, you don't want to measure here and then flip it over and measure here. You want to be confident the radiation, the background or the incoming radiation stays the same if you're going to using the same sensor, and then invert it because the measurements are separated by time.